This is going to be the second part of the January 2024 paper of Physics Unit 1, Mechanics and Materials, Edexcel International A-Level. So this was taken in January, and people who need to retake it, the exam is next Friday. So that will be the 10th of May. So this will help you go through your own answers. If you've done the January 24 paper and you want to see where you went wrong, please take a look, like, share and subscribe with your friends so you get more people to watch our videos. We now have over 150 subscribers, and we only started making videos, I don't know why I'm saying we, me. I started making videos in January, late December. Okay, so the first part we did questions 1 to 15. It was a 37-minute video. It should be uploaded soon. Video 2 is going to be the longer questions, which is questions 16 to 18. I think it's only 18 questions, and hopefully that will take 30 minutes or so. Okay? So here is question 16. It's about skittles. Skittles is the old form of 10-pin bowling. So a skittle is a wooden object that can be stand upright on one end. So here they are. They haven't got the heads like they've got in 10-pin bowling, and those heads are probably because in 10-pin bowling they automatically get taken by machines. The original skittles were this shape. In a game of skittles, a ball is thrown. Here's the ball at some skittles to knock them over, as shown. Okay, so modern day we have 10-pin bowling. The diagram shows the ball just before it collides with the skittle. So imagine the ball is going that way. So the ball has momentum, the skittle doesn't. So it's about momentum. You can already guess what they're going to ask you. It then gives you a graph. The graph shows, how the velocity of the skittle varies with time. So obviously before the collision, it doesn't move. And as the skittle collides, so the collision must happen here because something happens, the velocity of the skittle here starts increasing. At first slowly, then constantly, and then stops increasing there. So that's how it varies. So this must be when they have made contact. They must be making some kind of contact at this point. So you can work out how much time it took for the collision. The time shown on the graph starts just before the ball hits the skittle. So this is just before, this is the collision, this is when they stop interacting. Okay, so this gives us time and velocity. Okay, so here I've estimated the time here to be 15 milliseconds and the time here to be 48 milliseconds when it completely becomes a straight line. The velocity here I've estimated to be 2.85 meters per second, and obviously the velocity here at the initial contact would be 0 for the skittle. Okay, so once we have this information, we can probably start solving the problem. They want you to determine the average acceleration of the skittle during the collision. So if the skittle collision is from the first point of contact here to here, then you need to use the full values from there to there. Okay, so once you've done that, the values I've showed you before, the final velocity was 2.85 meters per second. Initially it was 0, so the change in velocity is 2.85. So you could have also written this as delta V if you wanted to. So delta V is 2.85, delta T is a difference in the time between them. Remember, they're both in 10 to the minus 3. I didn't point that out. So the time is in milliseconds. So that means 10 to the minus 3 seconds. Okay? So once you've done that, you put the numbers in to 3 significant figures. It would be 86.3. So here I've got 3 significant figures, but most of the data is 2 significant figures. So I think you're right and correct also to round it up to 2 significant figures. So I always recommend to my students, when you're calculating it, show with 3 significant figures, and then here you can put 2 significant figures. And then obviously that shows the examiner that you're aware of the significance of significant figures, if you pardon the pun. And then, now, this is an asterisk, so 6 marks. Explain how Newton's second law and third law, that's 2 laws of motion, apply to the ball and the skittle. during the collision. So I'm underlining it's Newton's second law and third law to apply to the ball and the skittle during the collision. So you've got to explain. So at 15 milliseconds on the graph, I put, this is not necessary for the mark on the mark scheme, but it's part of the clarity of your answer. And remember, anything with asterisks is the quality of your written communication, your reasoning, and your logic. So at 15 milliseconds on the graph, that's really specific, the collision occurs. And the ball applies a force on the skittle. Okay, 1 mark. According to Newton's third law, I've said, forces must occur in pairs. And force, third law, for every, I said 4, I thought I'd written 4, force. For every action, there is an equal and opposite reaction. Okay, so I think that will get you a second mark, which means as the ball applies a force on the skittle, the action, the skittle reaction applies an equal in size and opposite force on the ball, i.e. opposite in direction. I think that'll give you a third mark. So this is all Newton's third law. Okay, so these two equal and opposite forces, I've said, apply a resultant force to each object, ball and skittle. Okay, so Newton's second law is looking at one object at a time, whereas Newton's third law is talking about the action, reaction, interaction. So I always say to my students, even in GCSE, that really Newton's third law is the starting point, and then Newton's first law and second law is whether the forces are balanced or unbalanced. And Newton's third law leads to Newton's second law in a way. So each object, the ball slash skittle, then accelerates in accordance with Newton's second law. So one will accelerate, yeah, and the other one will decelerate. Obviously, the ball is giving momentum to the skittle, so it will lose velocity, it will decelerate. So the ball will decelerate and the skittle will accelerate. The skittle accelerates to the left while the ball decelerates. Obviously, it was still moving to the left, but it will be at a lower velocity. And I think if you put all this in a clear fashion, you will get all 6 marks. Now, if you look at the mark scheme, and I'll show you it, you get, for these questions, you can only get 4 marks for just listing these points. So the 2 extra marks, number of marks awarded for the structure of your answer and sustained line of reasoning. 2 marks says the answer shows a coherent and logical structure with linkages and fully sustained lines of reasoning. So I think mine would get 6 marks, obviously. But if you put all these and you've done it the way I've done, you'll be fine. Okay? While you're at it, here's part C. So you can stop the video and have a look how part C is about. Looks like it's a calculation that you need to do for part C. So you can pause the video, have a look at the mark scheme, so I don't have to put it back on again afterwards. So there means there's a final part. 16 part C. The ball is thrown again, it says. We're talking about skittles still. The collision collides with another stationary skittle. During the collision, the horizontal velocity of the ball changes from 7.2 to 1.6. So it changes from 7.2 to 7.6. That's a change in velocity. The horizontal velocity of the skittle immediately after collision is 3.1. Obviously, we started at 0, so it'll be a change in velocity. So this is something giving you numbers to do. Yeah? And once you got those, they want you to determine the mass of the ball. The mass of the skittle is given to us. So we know the velocities. We know that one of the masses we have to work out the second mass. So what is this about? It's the total momentum before the collision must be equal to total momentum after the collision. So obviously the momentum before the collision is just due to the momentum of the ball. So this was a U. I put V by mistake. So initial velocity of the ball times the mass of the ball, yes, which is what we want to work out, plus the mass of the skittle, the momentum of the skittle initially, which is 0, because it wasn't moving, will be equal to the mass of the ball times the final velocity of the ball, plus the mass of the skittle, which is now moving, times the velocity of the skittle. Okay, so we know Vs, we know Vb, we know Ms, and we know the initial velocity of the ball. Okay, so the ball changes from 7.2, so we know U is 7.2. If you put all the numbers in, so I've taken this on the other side, put the ball ones together, because we know that it changes from 7.2 to 1.6. So I can then factor out the mass, because this is what we want to work out. So you can see what I've done. I've just done a bit of algebra. And on the right-hand side is just the mass of the skittle. So the loss of the momentum of the ball becomes the momentum of the skittle, in other words. So this is how much the velocity changes. The mass doesn't change, so we can then divide the 7.2. We can put this on the denominator, which is 5.6, multiply it to 3 significant figures, you get 0.775. And if you want to round it up to 0.78, which is most of the values are given 2 significant figures, you probably should put it to 2 significant figures in this case. Okay, so that is question 16. Okay. Question 17, then it says a student determined the Young's modulus of a material in the form of a wire. Okay, the student used the micrometer to measure the diameter of the wire and you should describe how the student should check that the wire is uniform. Yeah, because obviously the wire is made by a machine. So this means you've got to measure with a micrometer at different positions along the length to make sure that it's of uniform thickness or diameter, and check that the wire has a circular cross-section. Well, this means make sure that you do it at different angles or different orientations. So if you mention different positions along the wire, that will check that it's uniform. If you do it at different angles of the wire, you can check that it actually is circular. Okay, so you can see the mark scheme for question 17 to make sure that I haven't missed anything. So question 17, there's the mark scheme, so you can see that's how you get it. You can also pause the video for parts B and B1 and B2. Okay, so there's question 17, first part. Then it comes to the nitty-gritty, the data, the setting up. So the student hung a reference wire. So this is the reference wire which is holding the fixed part of the vernier scale. The vernier scale, you'll notice this has got 10 points on it, and they're slightly non-aligned with the 10 points on the scale here. And that's how a vernier scale works. So you need to make sure you know how a vernier scale works when you're measuring it in the lab. Okay, but for this question, you just need to know that this is the reference wire, and then this one will be you add more weights onto this one. So as you increase the mass, this one will slide down against the starting point. So you've got to make sure there's usually an adjustment screw on this, which allows you to make sure that you're starting exactly with the 0 lined up with the 0, so you know you're starting from you don't have a 0 error. Okay. So you basically, it's all hung from a ceiling, so these wires are quite long. They're over 2 meters long usually. At the lower end of the wire, they're positioned of the fixed part of the vernier scale, which I said. The student then attached a 100-gram mass, it's here, which I think is rather low. It means the wire is not very thick. Sometimes I've done it with actually kilogram masses. So the wire being tested, the initial reading on the vernier scale is 0.0. So basically this is 0.0 means the zeros are lining up. Okay. As shown, he added masses to the mass hanger and measured the corresponding extensions. So basically you're going to measure it with this and get values accurate to 0.1 resolution. Yeah, of a vernier scale. Resolution is 0.1 millimeters. Okay. So that's what you will need to know also for practical skills. I think this is a core practical, Young's modulus, isn't it? Anyway, the student kept his feet away from the apparatus so that masses could not fall on his feet. So you've got to explain one other safety precaution. So obviously masses falling on feet is important, and you normally have to put something like a rubber mat or sponges underneath, like those thick sponges that you can get in the labs. So another one would be goggles. Why? Because it could snap. So again, I've shown you the mark scheme, have a look. So the explain means you're explaining about safety goggles. You must wear safety goggles when you're doing this, because at some point the wire could snap and it could go into your eye. So you want to protect your eyes. Okay. Obviously you can also cause a scratch if it hits your arm or whatever, but your eyes are the most important part to protect. Part 2. Each time the student added more masses, delta x increased by a few millimeters as expected. Explain why he should measure delta x using a vernier scale instead of a meter ruler. Well, a meter ruler only has a resolution of 1 millimeter, whereas the micrometer vernier scale has a resolution of millimeters. Okay, so explain why. So yes, the resolution is smaller. So what difference does that make? It makes the percentage uncertainty will be smaller. If the resolution is smaller, the percentage uncertainty will be smaller. And again, I've shown you the mark scheme, so you can go back at the earlier part of the video, freeze it, check that you got your answers right. Okay, it then gives you the data. The data has been plotted as a graph. Okay, now they've done it deliberately just to confuse you. They've put force on the x-axis and extension on the y-axis. So, and you'll notice here it doesn't quite go through the 0 point. So it could be some kind of systematic error in the instrument. So that could be a question they ask you in the practical skills. It should really go through the origin, or is this the initial 100 grams that they put on? But it shouldn't be, because the extension should be 0. Remember, it was 0? So this looks like they got some kind of 0 error when they've done the line of best fit. Okay? So you don't force your line to go through the origin, you do the line of best fit and then deal with it, and you comment on it and you evaluate the success of your experiment. The other thing I want to show you is how I've drawn the dotted lines here to show how much the x has increased on the graph and how much the force is increased on the graph. You want to have the triangle as large as possible, so when you're working out the gradient, you get a lower percentage uncertainty in your value. So you can work out the gradient of this, but obviously the stiffness of the wire would be 1 over the gradient, because stiffness is basically F over delta x, yeah? And that means it will be equal to 1 over the gradient, because this is delta x over F. Okay, so that's part C. They then give you information in a table for 3 different materials of their Young's modulus value. Remember, Young's modulus is stress over strain. If you actually work it out, stress over strain can be force times the original length times the cross-sectional area divided by the extension. Okay, so I always remember it as flax. Yes, so you can go straight into that, and I'm going to use this equation rather than work out the stress and the strain, but you can do it either way. Deduce which material the wire was made from. So in other words, we want to work out the Young's modulus. Okay, so I'm going to use the Young's modulus equation directly from the graph. Now remember, the graph had x over f. So we know this value from the gradient. We can inverse it. So now we talked about the gradient. So f over x is 1 over m. And we've been given the length, and we can work out the area. So ultimately, we know the gradient from the graph, with the length has been given to us as 1.80. So you just put that value in. And the A, you can work out. So once you do that, you can go straight into it. That's why I like using this method, rather than have to calculate strain, stress, and strain. So this gradient is a quick way of getting the answer. Okay, so the gradient from the graph will give you the values I've shown you. If you look back at my graph, you can have a look. You can stop the video, 10.4 times 10 to the minus 3. Why am I doing 10.4 times 10 to the minus 3? Because it's in millimeters. So that's 10 to the minus 3 in meters. Okay? So remember, you have to use SI units if you want to get Young's modulus. So once you've done that, you divide it by the change in force, and you'll get the gradient. And remember, F over x is 1 over the gradient because of the orientation of the graph. And you put that number in. Here's the gradient. And so the only thing to remember is how to work out the area. The cross-section area is pi r squared, which is d squared over 4. Okay? Put the numbers in, you'll get the area, and the green ticks are showing you where you get the marks from on the mark scheme. You do that, it comes out to 1.067 times 10 to the 11 pascals, which is approximately 106 gigapascals, which is closest to the value in the table. It's actually, obviously, it's approximately equal to 107 gigapascals, which is more or less equal to the value given in the table for brass. So you conclude the material could be brass based on the data provided. Okay, hope that makes sense. So that's a good question to revise also for Unit 3, because it has got the skills you need for resolution, etc., uncertainties. Okay, so what we're talking about next is the final question, which my students said they found the most tricky. So I'm going to go through this one with you next. This is a door. It's got 2 hinges. and obviously the door has its own weight. The weight would act through the center of mass, which would be, if it's a uniform door, would be the diagonal where the diagonals across there meet, so that would be the center of the mass. So that would become the weight. Okay, so uniform door with a width W and hinges X and Y. So obviously the hinges are keeping the door up. Yeah. So you've got no resultant forces. The forces upwards, yeah, are equaling the weight. Yeah, and then also the forces left and right must be balanced. Okay, so this is a no resultant force. So what equilibrium, there are two conditions: no resultant force in any two directions, yeah, in opposite directions, and no resultant moment about any point. Remember, moments can be taken about any point to suit you to solve a problem. So they're given the length between the hinges and they're given the width of the door. Okay, so we're going to take moments at some point. The other thing they want you to know is what does seems to be a common question in Unit 1, give the meaning of the term centre of gravity. Well, the centre of gravity is the point at which the weight of an object, example in this case the door, is considered to act from or through. I like to make sure you put this in because I think it clears up the English. Okay, it's considered to act. It doesn't really finish off the sentence. Okay, it acts through that point, the weight. Okay, or it acts from that point. So when we're doing our equations, for example, we want to take moments. We're looking at weight acting through the center of gravity. So we know, for example, that the perpendicular distance there is W over 2. And remember, we know the distance there is length. Okay, so we have all this. It's not to scale, but you know the values. And here we know that they told us one force is acting this way, one force is acting this way. That means the component of this force acting that way must be equal to the component of force acting this way, because to accentuate the point that we made about equilibrium. Okay, in any two directions the forces must be balanced, and that means also the component of this hinge force upwards must be equal to the component of the component of the force upwards here plus the component of the force upwards here must equal the weight downwards. Okay, that's these two forces upwards, vertical, are balancing the weight of the door. Well, we know the weight of the door is simple. You just can work it out. It's 141.3 newtons. So I've put it to one decimal place and it's approximately 141 newtons. Okay, why am I putting it to 141.3? I just wanted to check whether this value later on is exactly 60.0. Which is given in the mark scheme. So they've given you the weight of the door and they want you to show the horizontal component of the force of hinge Y. The horizontal, they want you to work out this one. Okay, the horizontal component, yeah, of the hinge force, which is at an angle at this direction. Okay, they haven't given us the angle, so we've got to do some work on that later on. Okay, so we know we want the size of the force. Okay, so if we take moments about x, that means we don't need to know the forces at x. So you should take moments at the unknown position. That eliminates the need because the perpendicular distance of the force at x, which is this, 2x is 0, so the moment will be 0. So the moment of the force here can therefore be ignored. So then you say the clockwise moments, sum of the clockwise moments, sigma, means the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. So clockwise is the direction the clock moves. So if we take it, this is the center of the clock, this one's going clockwise, and horizontally this one's going anti-clockwise. Yeah, so this one's going this way, anti-clockwise, and this one's going, the weight is going clockwise. Okay, so there's clockwise moments and anti-clockwise moments. Okay. So that's what you need to make sure you use an analog watch. Here I have an analog watch, okay? So the force, the horizontal that we want to work out, the perpendicular distance of this force, 2x is 1.6 meters. So that's the perpendicular distance. And W, the perpendicular distance to x, yeah? And that means it's the perpendicular distance from the line of the force. So it can be, there it is, W over 2. Yeah, so this is also W over 2. So we know the perpendicularness of the weight, we know the weight is roughly 141, and we know the width given to us before is 0.85. So it's 0.85 divided by 2, so it comes out to 60. 60 divided by 1. So 60, sorry, you couldn't see my answer, I apologize. 60 divided by 1.6, algebraically, it gives you the force horizontally, yes, of 37.5 newtons to 3 significant figures. 3 significant figures, 3 significant figures, or 2 decimal places. I think that's valid to keep it to 3 significant figures. Okay, that's part C. Okay, then part 2, now they want you to work out the angle. Then the vertical components of the force of each hinge, I've already explained to you, on the door is obviously equal to half the weight, they're saying. So they're telling you that the vertical component of each force, yeah, so this vertical component of X and the vertical component of Y are basically taking half the weight each. Remember, the weight was acting downwards. Okay, so hope that makes sense to you. The hinge Y exerts a force on the door at an angle theta. Here's the angle theta. They want you to work it out. So that means this angle is also theta. Okay, so you can now do some trigonometry. So you know that FV is W over 2, which is 141.3. I'm using the accurate value over 2. And we know FV is F cos theta. Okay, so that would be F cos theta. So the vertical force is also there. And you're going from F through the angle. So it was cos, F cos theta must be equal to W of 2. We know the horizontal force from before. We know the W. So we know this. And we know this. The only thing we don't know is cos theta. And you can therefore work it out. You can also do the square root. You can do the square. So we want to work out the vertical force. So there are different ways of solving this problem, in effect. So you can also do FH squared plus FV squared must be equal to F. So you can work out, they don't want the horizontal, they want you to do the total force. So once we've done that, we can work out that this is 141.3. Yes, so this is where we're getting that value from. We know that F vertical from here. I should have put the values in for you, but that's what it becomes, 141.3 divided by 2. You'll have to try and do that yourself. So this is Pythagoras. Yeah, so we're using Pythagoras, two sides of the right angled triangle. So FV squared plus FH squared must be equal to F squared. We know FH squared and we know FV squared now from the angle is 141.3 divided by 2. Square them all, you get 80 newtons exactly. Okay, and then tan theta is going to be opposite over adjacent, which is 37.5 divided by what we just worked out. Yeah. No, divided, yeah, we could have done the other way. Divided by what we had worked out before, which is 141.3 over 2. And you can work it out as 28 degrees. So you could have also done, you didn't have to do tan, you could have done, because we now know F, you could have done 37 over F, which would have been opposite over hypotenuse. You could have used sine. Okay, anyway, once you've done that, you put your values in there. I've put it to 2 significant figures and you'll get the marks. Okay, so that's part C, part 2. C, part 3, the final part of the question and the final part of the exam. The identical door is supported by hinges that are much closer together. Explain how a smaller value of L, that means the distance between the two hinges, affects F and theta. You should consider moments about point X. So point X is exactly where we took moments about before. So we know from before that if you take the moments about point X, we don't have to think about the forces at X, but we have the horizontal force, which is what we wanted to do. The horizontal force times the length between the hinges is equal to the weight times half the width of the door, which we knew was approximately 60. Yes, as the weight of the door doesn't change. Okay, half the weight of the horizontal component. So once we do that, so you don't really need to put this bit in, so you know that. So if L decreases, W doesn't change, yes, that means FH would have to go up to compensate for it. Okay, so this would have to increase, so you get 1 mark for that. Assuming FV at each hinge still takes, Yeah, half the weight as before. FV doesn't change. If FH increases, FV doesn't, then tan theta will increase. So theta will increase. Okay? So that's basically how you prove the point. Yeah? So I hope that makes sense to you. You need to look at it in combination with the diagram on this page. Yeah? So if FH, we said, would increase, so this increases, that obviously means the angle would be bigger, so this will go further, so the angle would therefore also get bigger, okay? Because FV, we're assuming, doesn't change. So that makes the angle of the triangle bigger. So I hope you found that useful. So make sure you go through it, your own answers, correct your mistakes, and then do some more practice papers before next week's Unit 1 exam. Good luck in that next week. Okay, the more papers you do, the more mark schemes you look at, the clearer your answer will be, and I hope you find my writing clear enough to read. Thank you for watching, and please like, share, and subscribe so you know when the next videos are going on. Please also do some Unit 3 practice because that really helps. Okay, hopefully see you in the next video. Bye for now.